Good afternoon, everyone. We're the FUNSAT design competition team. My name is Jonathan Groot. This is Frosik, and that's Elijah Newman. So basically, our goal was to design a cube satellite to take part in the FUNSAT design competition. We're following basic constraints set forth by the competition. We have weight constraints and size constraints that you can see there. So what we're going to be doing in terms of the structure, we're going to be lightening the structure. We're going to be making a strong structure, making it more accessible during testing and setting up phase where we can access all the components inside to make that go smoothly. We're doing the orbit and power simulations, and also the control systems. We're doing a mechanical valving system to control the altitude, which is the height of the satellite during testing, and the attitude control, which is the orientation of the satellite during orbit. When we approached this project, we basically went ahead and used all previous competitions and previous papers and other CubeSats, saw their designs, and we decided where we could make improvements and stuff to that. Starting with the structure, I will say that we are following a Senior 2 team. They're right now taking part in the FUNSAT design competition, so we were supporting them. And then we're going to go ahead and continue it, hopefully have our own independent launch in December. One of the things we wanted to do was take their designs, similar designs, and improve on the structure, its load-bearing capacities, and that kind of thing. We started off by saying we were going to make the inside structure modular and removable, so we can remove all the components while we set it up to make that go easier. But as we went on, we realized we had a space constraint and we didn't have enough room to have those modules removed. So we made everything fixed inside. We made it out of aluminum because it's strong and lightweight and it's very easy to work with. So the main thing about doing the structure, we had to come up with a way to keep the center of gravity of the structure around the geometric center of mass. That way, during orbit, it's easier to control. What that basically entailed was finding all the components we hope to use, finding rough size dimensions, creating solids, seeing the masses that we need to have for each one, and coming up with a resulting density in our SolidWorks simulation so that we can simulate that. As you can see there, that snapshot is of the center of mass that we have, showing you the x, y, and z coordinates of that center of mass. And ideally, this is what we were looking for. So we came very close with how we arranged it in the structure itself. So this just basically shows you like the different designs as we went through. The first one was the previous Senior 2 satellite that they had done. We went on, we made the structure itself with holes to reduce the weight of the satellite itself. This image here just goes and shows all the components packed inside and the tight constraint you have with working with these components in order to keep the center of mass around the geometric center of the satellite itself.
The mission of the satellite is going to be to perform ground imagery for such things as weather prediction, cloud height formation, the thermal imaging as well. It's going to have a thermal camera. Now, in order for the mission to be successful, the orbit needs to facilitate the mission. For effective ground imagery, we use a polar orbit. The reason for this is because you can see this is for one orbit. Multiple orbits would cover lots of ground. We use an orbit of 600 kilograms. The reason for this is because we want to minimize the small amount of drag that's going to be acting on the spacecraft, and that's going to allow us to have a mission that's active for a long period of time. Now, the orientation of this orbit is in the plane of the sun as it shines on the Earth. That's called the dawn-dusk orientation. And what that does is it means that the sun is going to be shining on our solar panels for every point through the orbit. So that allows us to do energy balance and based on that constraint, and also allows us to minimize the size of the battery. We did a power simulation for how much energy is going to be generated by the solar panels using the SDK software. That's the same software that generated those orbital pictures you saw on the previous slide. And this is based on a solar panel with an efficiency of 29.3%. With these solar panels, we have a maximum power generation of 8.5 watts. We have a minimum of 7 watts. Thanks to the dawn-dusk orientation, we do not have any point where we drop into shade and therefore have zero power generation.
Okay, so going into the control system, so attitude control system. Attitude is the means by which the satellite will actually control its pointing and orientation when in orbit. There are many different types of attitude control, but given the size and weight constraints for our satellite that we're working on, we're going with magnetic torquers or magnetic torque bars. Now, magnetic torque bar is basically a copper current kind coil with a soft magnetic core material. And of course, when a current is passed through this coil, a resulting force is produced, which acts on the body of the satellite, thus shifting it. So the design process for the attitude control system, of course, we're concerned with the torque, which is a function of the magnetic moment and the magnetic field produced, and of course the force, which is just obtained by dividing by the radius of the core that we're using. So basically, we define a wire length and a voltage, and also the core radius and the length of the actual torque bar. And going from this, it's just a matter of creating an Excel sheet and messing with the values to obtain a force. So when we obtain this force, what exactly does it mean? What are we comparing it to? So basically, defining a velocity and using impulse momentum equations, we can actually calculate a force that would be required to shift the satellite by a certain degree in a certain time reference. So with a velocity of 7.55 km per second, which is obtained from the orbit calculations, we have a force of approximately 24 newtons that would be required to shift the satellite 1 degree. So in our final design here, with a core length of 9 cm, which is the width of the satellite, and with a total of 8,000 coil turns around that bar, we actually obtain a force to match the 24 newtons, which would imply that we can actually shift the satellite 1 degree in the time frame of 22 seconds. Of course, this is yet to be tested, and this is just the design that we have for right now. So this valve system that was mentioned before, what exactly is it? During tests of the satellite, what we do, we actually attach it to a weather balloon, and we send it up, and then when the weather balloon pops, of course, we collect the satellite and then collect the relevant information. The idea behind this is to actually attach a valving system consisted of a pressure relief valve and a drain valve that would attach to the weather balloon. And what that would allow us to do is actually control the flight time by telling the weather balloon to release pressure by telling the valve to release pressure from the weather balloon at a certain height, so as to maintain or try our best to maintain a certain height to prolong lifetime. And of course, the drain valve to, after a certain time, drain all the air from the weather balloon for it to actually fall back to Earth to collect relevant information. So for technical standards, since it is a NASA competition, we reference NASA's technical standards. Highlighted are the 3 that we'll be focusing on, but as we go into actually building it and developing it, actually we will have to be referencing all of them. For global design, of course, satellites are a relevant tool. They're a researcher's tool, and we will design our own in such a way where it can actually be attached to any launcher in any part of the world. It's not going to be specific to here. All models and drawings were done in industry standard programs, Satellite Toolkit and SolidWorks for modeling, and we also plan on building using readily available materials that don't require any special manufacturing skills as such to make.
This is a Gantt chart that shows our project organization. We spent these last few months designing the systems that we just presented. We're going to continue developing them in the summer. Should have our prototype ready by October so we can start doing tests with the weather. Going forward, we're going to build on the systems that we mentioned. We're also going to develop other systems that are necessary for the satellite. That includes establishing communication with the ground station, making sure that our payload is working correctly, integrating all the systems from the systems perspective. This is the #1 cause of failure, so we have to spend a lot of time on that. And fabricating it and finding somebody to launch it. If we win the competition, they will launch us. So that's what we have to look forward to.
Any questions? Comments?
So this will be a payload in a rocket launcher.
It's going to piggyback onto a bigger satellite that's launching into a similar orbit.
Okay, so the question I have for you is, have you compensated for rapid acceleration in the design to ensure that your device doesn't tear itself apart on liftoff?
Yeah, we did that. We did calculations given what we researched as the acceleration and stuff that the rocket itself will withstand, and we're going to do testing of the structure and all the components to make sure that it withstands that temperature. I think it's something around like 90 Gs is what it's expected to withstand. Yeah.
Okay, and on the valving system
Yes.
itself, how is that controlled?
The valving system, it would be a pressure relief valve. Again, we haven't really looked too much into that just because the competition is happening right now. So that was just an idea that we had that we kind of placed on the back burner for now. We're focusing on developing the relevant systems that would actually be used for the satellite. But the idea we have is a pressure relief valve, just a mechanical pressure relief valve. And the plan is to adjust pressure or change the pressure on it so that at a certain height, you'll know the pressure difference. We can predict the pressure at a certain height so as it will to release.
So it's a
air.
purely mechanical system.
Yeah.
Right, that's the idea that we have as of right now.
Just like to point out that is strictly during testing. We found that, yeah, this is going to be for the competition. That's not going to be used when it's actually launched into orbit. But testing is a big part of making sure that all your systems work. And currently how it works, it goes up with a weather balloon. The weather balloon pops and it comes back down. We want to be able to control that height during testing. So we're going to go forward during testing phase and do that. Where we do our calculation, see how high it's going to go with the amount of helium we put into the balloon. And we said it's going to be a preset valve that releases, so it never reaches the temperature of where it pops. So we maintain that, and then we have to have another valve that releases all the air after a certain amount of time, all the helium after a certain time, so it comes back down. If not, it's just going to travel forever. So that's
Okay,
strictly
where
during
can you
testing.
test these things?
The senior 2 team, they had done previous testing out in like Nevada and stuff in desert areas. That's mainly where we tested. They said you can do it in Florida, but there are a lot of restrictions with where we can fly it over. So it really involves a lot of like California stuff with big open test sites that we can go
And
test
that's what
on.
your plans are?
Yeah.
Thank you.
Any other questions? Comments?
What's the chassis made out of?
It's all aluminum.
That looks like 80/20.
I think we were using, we did some testing before, and I think we used 6061. So that's what we're using now. Anyone else?
Thank you.
Thank you.
Next, we will